Okay, so let's imagine we've got a water molecule here. So we got oxygen, hydrogen, hydrogen. So this end's slightly positive, that end is slightly negative. And so that means it's going to have a dipole moment. Okay, well, the dipole moment for a water molecule is 6.17 times 10 to the minus 30 coulomb meters. Okay, now let's say we have our water molecule here and we put it in an electric field of 330 newtons per coulomb. What's going to happen? Well, the water molecule is going to experience a torque. Okay, so we know the torque is going to be P cross E. And so the question is, if you exert a torque, it's going to rotate. Now, if we assume our water molecule starts like this, okay, and ends like that, we've rotated it. Okay, so we had to do work on it to turn it. Okay, so the question is, how much work did we do turning this? Okay, so you think back to physics 1. You apply a force, you know the work is integral of F dot X, okay, F dot dx. Well, in this case, it's torquing, so you remember how that works for torque. You just basically interchange variables, so it's integral torque d theta. Okay, and so again, that's going back to physics 1. Remember, physics 2 is just a continuation of physics 1. And so if I want to find the work that we did torquing it, then I would have to look at that and say, okay, so the work is going to be the integral of the torque d theta. Okay, the torque is going to be Pe sine theta d theta. Okay, and if we assume that we start with it at the angle of theta is 90 degrees, so theta naught is 90 degrees and the final theta is 0 degrees, that'll be going from 0 to 90 degrees. Okay, so we look at that and we know how to do integrals. This is going to be Pe times the integral from 0 to 90 degrees of sine theta d theta. Okay, so that's going to be Pe times the integral of the sine is minus cosine, okay, evaluated at 0 and 90 degrees. So that turns out to be, interestingly enough, just 1, okay. And so this is going to be P times E, okay. And because, you know, it's going to be 1 because cosine of 90 degrees is 0 minus the cosine of 0, okay. So, so negative is going to give you 1. So, well, we have those terms already. So we just multiply 6.17 times 10 to the minus 30 coulomb meters times 330 newtons per coulomb. And so the work done to turn this thing is 2.04 times 10 to the minus 27. Okay, now let's make sure we get the units right. Don't just write down units, check to make sure the unit's right. So we have coulomb meter times newton per coulomb. The coulombs cancel, newton times meter is joule. So the units actually come out right, which means we probably did something right. So the answer is 2.04 times 10 to the minus 27 joules. Now, the interesting thing is that your water molecule, you can torque it so that it's leaning over, but then if you turn off the electric field, all the other water molecules bumping it is going to knock it around. And so if a little while later it's back in that position and you turn on the electric field again, you're going to torque it again, which means you keep adding energy to it. The time that it takes to basically randomize, because what would happen if you had a whole bunch of water molecules, then the water molecules would be in all different directions here, okay, randomly, okay, And so what happens is if you turn on an electric field, then roughly about half of them get torqued. Okay. And so you add energy. Okay. Then you turn off the electric field, and then they randomly bump into each other. And if you turn on the electric field, once they get all randomized again, you add energy again. And so each one of them averages an energy about 2 times 10 to the minus 27 joules. The relaxation time, so the time to relax, turns out to be on the ballpark of about 0.4 nanoseconds, which means if you pulse it about every 0.4 nanoseconds, then you end up with you end up adding energy to it. Okay, so so the question is, how often does that mean that you're pulsing it? Well, that means you're pulsing it in the general neighborhood of, so in other words, the frequency would be 1 over the relaxation time, so that'd be in the neighborhood of about 2.5 gigahertz. Okay, that's a microwave, and so that's how microwave ovens work. And so they basically, you have this randomized association of water molecules. You pulse it with an electric field. You do a little bit of work. Microwave oscillates. A microwave is basically an electromagnetic wave. So it's a wave. So it oscillates plus minus. And so it's off. 0.4 seconds later, you're pulsing it again. And so you keep adding energy to it. And if you keep adding energy to it, then you start heating up. You add energy to the molecules and you start heating up the water. So that's how a microwave oven works.